Now let's consider something a little more detailed about the heat exchanger. Anytime you have a heat exchanger, there's going to be an analysis we need to perform to understand how it's working. And we have this idea of heat transfer resistance. So let's take the simple example of a double pipe heat exchanger. We'll cut it where we can see it. And so let's say we've got the hot fluid flowing through the center pipe and the cold fluid flowing through the shell side. Okay. Well, what resistance will there be to heat transfer? Well, there'll be resistance in the hot fluid in convection, resistance across the pipe wall in conduction, and resistance on the cold fluid side. Again, it's a fluid, so it would be a convective resistance. So you see the resistance equation there, and we could write the overall heat transfer rate as the driving force for heat transfer, the difference in the temperature between the hot and the cold fluid, divided by the resistance. Now, this is not the way we usually like to work with this type of equation. We usually like to work with it in terms of an overall heat transfer coefficient. You'll see why here in just a little while. Instead of writing it in terms of resistance, we'll write it as UA delta T instead of 1 over R. And so if you look at the equation at the bottom, usually you want the thickness of that pipe wall that separates the hot and the cold fluid, you want it to be as thin as possible. The reason is because you want its resistance to be as small as possible. And so the inner area, A sub I, of that little tube in the middle, where the hot fluid is in contact, and the outside area of that same tube, where the cold fluid is in contact, AO, they're often very close to one another. There's often not much difference in the amount of area in and inside and out. Now, technically there's a difference, so really you've got to base the UA product on either the inside area or the outside area. But most of the time they're so close that we just neglect that part and we just call it UA, because the area is so close, as I said before, inside and outside. But there's still some resistance in the wall that separates the two fluids from one another. Now here are some typical overall coefficient values for U. There's a table in your book, water to water, 850 to 1700 watts per square meter per degree Celsius. Now that makes sense that it's a fairly high overall heat transfer coefficient. It's two liquids exchanging heat. How about a steam condenser? Well, a steam condenser has an even higher heat transfer coefficient, or overall heat transfer coefficient. You may look at that and say, well, why would that be? Because isn't steam a gas? Well, yes it is, but what happens is when you have condensation or boiling processes in a heat exchanger, you find that they are very effective processes, because what happens is when steam goes and it touches a cold surface and condenses, that makes space to pull in more steam to also condense. So it's a very effective heat exchanger setup. If you have a gas-to-gas heat exchanger, though, almost at the bottom of this list, now we're at 10 to 40 watts per square meter per degree Celsius. And so the resistance to heat transfer is much higher, the conductance is much lower. But there's one other thing that we have neglected in our overall heat transfer coefficient. It is certainly possible that the inside surface of the tube and the outside surface of the tube that separates the hot and cold fluid will foul. And so there will be fouling resistance as well. And so I've brought back the resistance equation and included fouling inside of the tubes and fouling outside of the tubes. Now, most of the time, as I said before, the pipe wall is really, really thin. And it's also very, very conductive. So a lot of times we can basically just eliminate the resistance that pipe offers, or that tube offers, to the heat transfer, and just neglect it. And then the inner and outer area are approximately equal, they cancel out, and essentially the overall heat transfer coefficient can be written in terms of resistance to convection in the hot and the cold fluid, that's HI and HO, and fouling resistance on the inside and outside of the tube, which often is much more significant than the resistance to heat transfer via conduction through the tube. What are typical resistances of fouling? Well, here are some numbers for you in meters squared per degree Celsius per watt for various applications. But more particularly, what we're interested in is what can cause fouling. So if you have, like my boiler, you're burning wood, well, the exhaust gases are going to contain some unburned products. No matter how efficiently you burn, over time those products are going to collect and need to be cleaned off. They will be fouling. So those are unburned hydrocarbons typically. Okay, so That's one thing that can deposit and cause fouling. Other things are things like corrosion. When you burn wood, again, one of the byproducts is water, and so water can deposit on the steel surfaces and cause rusting and cause fouling in general. There can be mineral deposits. If you've never cleaned out your water heater, you should probably take this chance right now to go do it, because water heaters fail often in water heating elements because scale builds up, which is just fouling. It's just hard water deposits. You see, what happens is it turns out that water, for example, will precipitate out things when it gets hot. So if you take water and you heat it up, it's more likely to let things come out of solution, like lime deposits and things. And so mineral deposits can be a huge problem. And you know, the whole purpose of a heat exchanger is to heat something up. Well, you've got the perfect recipe there for fouling. So there are many plants, you know, that use say river water for cooling things, and if they use river water, there's going to be mud and silt in it. When I take you on a tour of the Cane Run Road power generation station someday, you'll get to see that they use river water for cooling their process. Now, their process is generating electricity from natural gas, so they're burning natural gas to drive a couple different turbines and things. But they have to use river water for cooling. So they bring in the river water and they don't use it directly. They actually have a whole building dedicated to processing that water to remove the mud and all the stuff out of it before it goes into the heat exchangers, so they can avoid fouling the heat exchangers for as long as possible. So corrosion, biological growth is another thing that of course flourishes in warm areas. And so all of these things can cause fouling. And basically, fouling always increases with increasing temperature and decreasing velocity. The velocity of the flow through the heat exchanger is important to keep relatively high, because even though that causes a fairly high pressure drop through the heat exchanger, it will help to mechanically remove some of the fouling and reduce the amount of time between cleanings of the heat exchanger.